Today we are going to discuss the first part of Chapter 8. We will study the atomic model and the atomic spectra. Today we are able to see the atoms. It was not the case about 70 years ago. In this picture we had a real image of the copper atoms. Today also we know the atoms are not the individual units but are made up of even smaller particles. However, we cannot see these particles of the atom as, for example, protons, neutrons, or electrons. Then the question is how it is possible that scientists can tell us about these very small subparticles if they cannot see them? The answer is they cannot observe these particles directly, but they can describe them and study their behavior from experimental evidence. In this picture, we have the timeline of the evolution of the atomic model. And we are going to review the story about the evolution of the atomic model in the last 2,500 years. We will study how and why the atomic model changed through the time. And we can see here in the timeline the evolution of the atomic model was important during the last 200 years. The concept of atom was first proposed by Democritus about 2,500 years ago. The main ideas of Democritus about the atoms were the matter could not be divided indefinitely. For example, this rock can be divided in small pieces, and you can divide these pieces again and again and again. But at some point, you cannot divide these pieces anymore. That is, the matter is discontinuous or made out of individual particles. For example, if this is a piece of matter, as what we had inside of the rectangle is a piece of matter, then the matter is not like that. It's not continuous. It's made of small and individual particles. Then the matter looks like that, according to more than 2,000 years after the concept of atom was developed by Democritus. John Dalton, who was a chemist and worked in chemical reactions, he proposed the 5 postulates that make up the atomic theory. And the first postulate says all matter is made of atoms. Atoms are indivisible and indestructible. An element is made up of identical atoms. And if you had a piece of gold, then that piece of gold has just gold atoms, one kind of atom. Different elements have atoms with different masses. And with this, he wants to say, if you had gold, then the atoms of gold has one specific mass, and it's not the same as the mass of silver, for example. Chemical compounds are made of atoms in specific inner ratios. Then, for example, if we had water, then that compound we had 2 molecules of hydrogen and 2 atoms of hydrogen and 1 atom of oxygen. And the last one say atoms are neither created nor destroyed in chemical reactions. This is related of conservation of mass. And his model was proposed in 1803, and the model he proposed looks like that, and it's called the Bohr model. Yes, just is the atoms are indivisible, yes, it's like that, and indestructible. After Dalton, about 100 years later, J.J. Thomson performed the cathode ray experiment. Let's see in what consists this experiment. Inside of the glass tube, in which most of the air was evacuated, he put two mirror plates, one negative plate and one positive plate. This plate was connected to a power supply. And what he observed was one ray came from negative plate toward to the positive plate. Also, he made a small hole in the positive plate, and he observed a small bit of electricity pass through the hole in the anode, and because he was coiling one of the sides of the tube with a special material, he observed a spot on this side of the tube. He was curious about the nature of the particles of the ray. He wants to know what are the charge of the particles of this ray he observed. And he conducted a new experiment. In this case, he put two mirror plates, one positive, another negative, close to the ray. And he observed the rays was deviated towards to positive plate. Then he concluded the ray must be made of the negative charges because we know unlike charges they attract. Then the only way this ray deviate if the ray is made by negative charges. These two charges will attract. So he concluded the atom had a tiny negative subparticles. What he did, he discovered the electron. In order to confirm this, the nature of the charge of the ray, he conducted a new experiment. In this case, he slid a magnet in the tube, and he observed that the ray was deviated in opposite direction, as was expected if in case of the negative charges. Based on this result, J.J. Thomson developed the plum-pudding model of the atom. This model consists of positive charged sphere with electrons set within it. We can think in this model as if we had blueberry muffin. The dough corresponds to the positive charge, and the blueberry corresponds to the negative charge. It means the electrons are embedded in the positive charge spheres, as is shown in this picture that showed the J.J. Thomson atomic model. Also, with this result, he proved the atoms are not indivisible as was proposed by Dalton. Also, using the magnetic data and electrical data, he was able to calculate the electrons' charge to mass ratio. Then he found the charge of the electron divided by the mass of the electron equals to 1.76 10 to the power 8 coulomb per gram. Then the important thing here, he discovered, not important. Let's see what was the contribution of Robert Millikan. He was able to calculate the charge of the electron, and because of that, he won the Nobel Prize in 1923. Let's see how he was able to do that. Then after J.J. Thomson, 2 years later, he conducted the oil drop experiment. He did the experiment using a chamber like this one. Inside of the chamber, he put 2 mirror plates. Then he connected these 2 mirror plates to a high voltage source. The high voltage was between 1 and 10,000 volts. Then he was able to regulate this voltage between these values. Then 3, 4. And this is the voltage multiplied by 3000. And he was able to regulate this voltage. Then what he did, he sprayed the oil drops inside the chamber, and after that he applied a voltage. What he observed when he applied different different values of voltage, and he observed for high voltage like 9,000 or 10,000, the drops was going up, and this happened because the force that acting on the drop was the electrical force that in that case was going up, and the gravity force was going down. If the electric force is larger than the gravity force, then this is why the drop was going up. And if the other thing he observed, if the voltage is small voltage, less than 3000, then the gravity force was larger, then the drop was going down. But what happened exactly at 3000, he found these two forces were equal, and he found at voltage equals to 3000, the electrical force was equals to gravity force, exactly at this value. Then the drops was stay still in this case. Then he was able to calculate the charge of these drops because he knows the mass of the drops, he knows the density of the oil, and he was able to measure the radius of these drops. He was able to calculate the charge of these drops. How he calculated the charge of this drop? Because he knew the mass of the drops and the voltage. He knew the mass of the drops because he knew the density of the oil, and also he was able to measure the diameter of these drops using the viewing scope. And using this data, he found the charge value for different drops, and these were the results. Let's see. For different drops with different masses, different sizes, then he got these results. 1 point for one of the drops the charge was 1.6. For other drop, he found this value. And then he found also this. He found also this value. And what we can see is what he observed was all the values are multiples of the first value. Then we can see is 1.6, 3.2, 4.8, 6.4, or all these values are multiples of 1.6. Then what he concludes is this is the fundamental charge, is the small charge that it is possible. Then he was able to calculate the charge of the electron. In addition, he calculated the mass of an electron using the Thomson charge mass ratio. Then see how he did that. And Thomson, he found the charge of the electron divided by the mass of the electron equals to 1.7584 10 to the power 11 coulombs per kilogram. Millikan, he found this is the charge of the electron. Then he combined these two results and he was able to solve for the mass, and he was able to calculate the mass of the electron. Ernest Rutherford, he won the Nobel Prize because he discovered the atomic nucleus. And let's see what was the experiment he conducted to find this result. Then he conducted the gold foil experiment, and the elements he used for this experiment was the source of alpha particles. Alpha particles are positive particles. Also, he used thin gold foil and also the fluorescent screen. This fluorescent screen allowed him to see the flash if the alpha particles hit this screen. And when the alpha and let's see the analysis that Rutherford did for his results and what were his conclusions. In this diagram, the circles represent the gold atoms and the arrows represent the alpha particles. Then we can see here most of the alpha rays pass through the material without any deflection, but some of them they deflect. Yes. Then he concludes if most of the alpha rays pass through the material, then atom is mostly empty space. Yes, this is the first conclusion. The second conclusion was if alpha particles that we know they are positive charges are repelling by something, yes, by something, then it must be positive charged. So he concluded there is a massive positive charge in the atom that later we know is he knew was a nucleus. Niels Bohr he won the Nobel Prize because he developed the planetary model of the atom. He based his model on experimental results obtained by Max Planck and Albert Einstein. He relayed the quantum concept and incorporated this to the Rutherford model. Then remember when we discussed the photoelectric effect, we say the Max Planck introduced the idea that matters emit and absorbs energy in discrete units called quanta. Also, Einstein, he extended this concept, this quantum concept to the light, and he said the light consists of discrete units called photons. These photons, the energy of these photons can be calculated in terms of the frequency of the vibration of these photons. Then we can calculate the energy of these photons if we multiply the Planck constant times the frequency. The planetary model developed by Bohr consists of three rules. And before explaining the rules, let's talk about this graph. And in this graph, the small dot we had here in the center correspond to the nucleus, and the other circles correspond to the orbits. Orbits are just energy levels, and the electrons can exist only in that energy levels. Now let's discuss the three rules. The first rule, the electrons only exist in certain allowed orbits. Then the electrons can exist only in these orbits. One more thing is the energy levels increase in this direction. This is the first energy level, this is the second energy level, and this is the third energy level. The second rule is that radiation is emitted or absorbed when changing orbits. Then the electrons can jump from lower energy level to high energy level if this electron absorbs some particular value of energy. And this electron can jump from this orbit to this orbit if absorbs some particular value of energy. In the same way, if the electron is in high energy level, then the electron can move to lower energy level only if this electron emits some particular value of energy. And the third rule is within an orbit, the electrons does not radiate. There is no radiation if the electron is in this part. To calculate the magnitude of the energy that is emitted or absorbed by the electrons when moved from one orbit to another, just we need to subtract the high energy level minus the low energy level. And for example, if the electron is in this and then move to here, then what we need to know the amount of energy that is emitted by the electron, then what we need to do is subtract the if we combine this concept with the Einstein equation to calculate the energy of the photon, then we can calculate the frequency of that radiation. Yes, we can calculate the frequency of the energy that is emitted or is absorbed by the electron. The current atomic model corresponds to the quantum mechanical model or electron cloud model. Two of the scientists who contribute to the development of this model were Erwin Schrödinger and Heisenberg. Let's see what was the Schrödinger work. He developed a mathematical equation that described the motion of the electrons in an atom. Based on this result, he proposed the atom was arranged of layer within layer in terms of the electron shells. It means we say, according to the Bohr model, we had energy levels. Yes, we had one energy level, second energy level, third energy level. But according to the Schrödinger results, the mathematical results, he found that each shell has some subshells. For example, for the first energy level, there are one subshell. For the second energy level, there are two subshells, or two suborbits also, we can say. For the third energy level, we have three subshells. His work leads to the electron model cloud. Heisenberg, he proposed surrounding the nucleus is a cloud-like region with electrons that move too fast and unpredictably. Then it's hard to find what is the location of these electrons. Then he formulated the Heisenberg uncertainty principle that states that we cannot measure the momentum means the velocity and exact position of an electron at the same time. What we can measure is the probability that the electron will be found in a certain region called an orbit. And this is how the current model of the electron looks like. Now we are going to talk about the atomic spectra. Let's see what happened with the white light. When the white light is diffracted, means it's passed through the slit and then through the prism, the white light is dispersed or is split into colors. Like a rainbow, the colors are continuous. We can see in this picture there is no space between colors. Also, we know the colors are associated with waves, and the waves, they have energy. This is why we can say the energy in the white light is over continuous range. Now let's see what happened with the light from an incandescent gas. Remember, incandescent refers when the objects emit light as a result of being heated. Then how can we heat a gas? And to do that, we will use the gas discharge tube. Inside of the gas discharge tube, we will put some gas, can be an element or compound, and we will apply high voltage. When we apply high voltage to the the discharge tube, we will see something like that. In this case, we had helium, neon, argon, krypton, and xenon. Then what we are going to discuss now is why the colors that is emitted by each of these elements are different. We are going to explain why this happens. When voltage is applied to the discharge tube, the excited atoms radiate energy. It happens because the electrons can jump up or can jump down. Depends on if they absorb energy or they emit energy. But the energy they absorb and the energy they emit is a special amount of energy. Is the difference between the energy of two orbitals. In this case, is the difference in energy of two orbitals of hydrogen. If the light that is radiated by the tube is diffracted and then is dispersed, what we can see here, if we had a spectrometer, we can see some lines. Then in this case, we don't have continuous spectra. We had just some particular lines. This energy is not over continuous range. The energy emitted when the electrons move from one orbit to another depend on the energy levels of the material, which are discrete values. The spectra produced is called line spectra, and it can identify each element or compound. It's like a fingerprint of them, means you can identify an element or compound by line spectra. Here we had some examples of the line spectra for different materials. We had for mercury, for nitrogen, for neon, and for hydrogen. And we can see each of these spectrum is different. And the reason is because the atoms of each element emit certain frequencies that are characteristic for each element. The last topic we want to discuss is what is the math and the physics behind of these lines. And we will do this just for hydrogen because hydrogen has just one electron. Then if the element has more electrons, the math and the analysis is more complicated. Then what we will do is we will just analyze the case of hydrogen. And let's apply what we discussed before. In this case, we want to solve this problem. We had an electron in a hydrogen atom jumps from the excited energy level n equal 4 to n equal 2. Then we want to know what is the frequency of the emitted photon and what is the wavelength of the photon. And we want to know what is the frequency of the energy that was emitted and what is the wavelength of the energy that was emitted. And what we want to calculate is if these are the energy levels and the electrons jumps down from here to here, then this will emit some photons or some energy. And we want to know what is the frequency of this energy, what is the wavelength of this energy. And to do that, we need to apply this equation. And to calculate the frequency, then we need to know the difference between the energy of these two levels. In this case, the high energy level corresponds to n equals 4 and the low energy level corresponds to n equals 2. And we need to know what is the energy for this level and what is the energy for this level. To know that, to do that, we will use this equation. We will apply this equation. And we know the innermost energy level, the E equal 1 correspond to, in case of the hydrogen, minus 2.18 10 to the power minus 18 joules. This value is just for hydrogen. This is just for hydrogen. And we can apply this equation, and we will calculate first the high energy level and the low energy level. Once we have these values, then we can calculate the frequency. Let's calculate the energy for the second level, and if we had N, let's slide here. And energy of the second level will be equals to energy for the first level divided by n, but n in this case is 2 to the second power. Then let's replace these values, will be negative 2.18 10 to the power minus 18 joules divided by 4. And then we will get negative, we divide this number, we will get negative 5.45 10 to the power minus 19 joules. Now let's do the same for the energy level. And we apply the same equation, we will apply this equation again. And in this case, the innermost energy level divided by n to the second power, but n in this case is 4 to the second power. And will be negative 2.18 10 to the power joules divided by 16. Then this will be equal to negative 1.36 10 to the power minus 19 joules. And now we have these two values. Now we can solve for the frequency if we apply this equation. And we had, if we divide by the frequency on both sides, sorry, if we divide by the constant value, then we'll have the frequency equals to divide by. And now we know this value, and we know this one. This corresponds to the energy for the energy level, for the second energy level, and then the constant value we had here. And let's replace these values. Let me write here, this corresponds to divide by, and the frequency value equals to, and now let's replace this value, will be negative 1.36 10 to the power minus 14 joules minus, then we have this negative here, and now minus 5.45 all this divided by the constant value is 6.63 10 to the power minus 34 joules per second. Now if we solve this one, here we have to be careful, negative times negative, finally we had here positive value, and you need to add these numbers together and then divide by h value, by the Planck constant. Then we will have 4.09 10 to the power minus 19 joules divided by 6.63 10 to the power minus 34 joules per second. We can see the joules cancel out, and we had 1 over second, which corresponds to hertz, and we know the hertz are the units for frequency. And if we solve this one, you will get 6.17 10 to the power 14 hertz. This corresponds to the frequency. And let me write here the frequency equals to 6.10 to the power 14 hertz. And we solved the first question. Now we need to calculate the wavelength. To calculate the wavelength, then we can use the equation of the electromagnetic spectrum waves, and this is frequency. We know the speed of the light, we know the frequency, then we can calculate the wavelength. And we divide by the frequency on both sides, and then we have the wavelength equals to the divide by the speed of the light divided by the frequency. Now just we replace the values. Then the wavelength equals to 3.00 10 to the power 8 meters per second divided by the frequency value 6.14 hertz. And now if we divide this, we will get 0.86 10 to the power minus 6 meters. And we have to here be careful with the units. We had like hertz is 1/second. Yes. I just because I don't have a space here, but we can do the units here in one side is meters per second, and because we had division, we convert the division into the multiplication and we flip the units. And seconds cancel out with seconds, and finally we had meters. And now if we write this one let's know in scientific notation, we want to write this one in nanometers. Then we want 10 to the power minus 9. Then we can move this 1, 2, 3 places. If we move to the right, we know we need to subtract 3. Then here the wavelength will be, let me write here, 486 10 to the power minus 9 meters, which correspond to 486 nanometers. You could remember 10 to the power minus 9 means the prefixes it correspond to nano. Then now we can write here the wavelength for this radiation is 486 nanometers. These are the wavelength and the frequency of the radiation that is emitted when the electron moves from the fourth energy level to the second energy level. Let's see if these values are close to the values we had in the diagram. And it's for 4 to the second energy level. And for the 4 to the second energy level, we had 6.2 10 to the power 14, which is very close to 6.17 if we write this number with 2 significant digits. And the wavelength is 484, which is close to 486. It's close enough. And this frequency and wavelength correspond to the blue-green color that we can see in the hydrogen emission lines. And this is all I had to discuss for today.